little mini projects during that period. And so it was in that course that Corey was exposed, I think it was the first time he may have been exposed to Pangaseus, or at least a variety of air-breathing fish in the Mekong Delta, and this is one of those animals. So he came back to Irvine, and after getting back to Irvine, he saw that, well, there's still just a lot of reptiles in the lab. So we thought, well, why don't we go back to Vietnam? And so I sent Corey back to Vietnam for an entire fall quarter to work at Can Tho University. And while he was there, he was with some other students, including some Danish students and Vietnamese students, and spent the fall of, I think, 2015, 16 in Can Tho. And so worked there, and of course, we set up here and collecting lots of data, and of course, liking the fish that we're there. And then later on, while he was involved in Can Tho and also in that course, he got to meet Mark Bailey. Mark Bailey is at Aarhus University in Denmark and works on air-breathing fish. And so when Corey got back to Irvine, applied for and got some money from the company of biologists, and then this, with the opposite direction, went over to Denmark to work with Mark Bailey at Aarhus. So here's a picture of Aarhus, city of Aarhus, and of course Aarhus University, and was able to work with Mark in his lab using some of the technologies and equipment they have to measure bimodal breathing in these animals. So it's a real pleasure today to introduce Corey, who's going to be talking about living in a high CO2 world, aquaculture, and fish that breathe air. And let me
Thanks for the introduction, Jim. So I picked the title "Living in a High CO2 World" to try to trick some of the ecologists coming in. But so this title is typically used for talks that are about climate change and how the atmosphere will increase due to CO2 being released into it. But I'm going to talk today about fish that lives in a truly high CO2 world, and that's this fish area, Pangaseus. Just to put this into perspective about the level of CO2 we're going to be talking about. Here's modern day CO2 in the atmosphere, so it's about 300 parts per million. If you convert that into millimeters of mercury, and that's just different units that physiologists typically use, it comes out to be about, well, it's less than 1. And if you look at sort of the worst case scenario or business as usual in terms of CO2 projections in the atmosphere, by the year 2100, we'll have about 1 millimeter of mercury. And up here is your breath, as we exhale about 40 millimeters of mercury. And all these dots here are CO2 levels that occur in aquatic environments. So animals like this fish here live in a truly high CO2 world already. And they're able to cope and survive in these environments. And it's important to learn how these animals interact with the environment. Because fish are important not only for our global food supply, but also for jobs and economic development, particularly in developing nations. And this is the State of the World's Fisheries and Aquaculture Report, published by the UN in 2018. And it has this figure here, looking at the amount of fish produced since 1950 to present day. You can see there's a steady increase in the amount of fish we're producing. And if we divide that into capture production, so the orange part is how many fish or how many million tons of fish we're capturing from the environment versus aquaculture, which is the blue section here. You can see the oceans pretty much are producing as much as they can since it's about the early 2000s. So they're pretty much being harvested at the maximum sustainable rate already. And this increase in production over the last couple decades has been really met by increased production in aquaculture. And so that's the farming of fishes. And this increase in aquaculture production has been termed the Blue Revolution. And it's been promised to not only decrease fishing pressure by providing a market-based substitute for wild capture fisheries, but also produce and be able to feed our planet in the most efficient way possible. And so here we have the feed conversion ratio for a bunch of different agricultural animals. And what this is the number of pounds of feed necessary to grow 1 pound of animal. So, for example, it takes 6.8 pounds of feed to grow 1 pound of beef, 2.9 pounds of feed to grow 1 pound of hog, and 1.7 from broiler chickens. And here we can see agriculture or aquaculture for fish in general. It's extremely low. So it's the most efficient way of converting feed into animal protein. So this is just one of the benefits of agriculture. And you can see in 2016, this is the first year where the amount of fish we consume worldwide by aquaculture has outpaced what we have captured from the ocean. And that trend is only expected to increase to 2013, or about 60% of what we consume in terms of fish has been projected to be from aquaculture, and only 40% from wild capture fisheries. And a lot of this growth in aquaculture has occurred in Asia, and particularly Vietnam. So Vietnam, as a single nation, has really outpaced in the last 2 decades these other continents. So you can see the Americas combined is less than Vietnamese aquaculture production, and so is all of Europe. And if you look at what species are being produced, here we have what we typically think of aquaculture species. This is a rainbow trout, and so it's a temperate freshwater species. It's black line here. And you can see the increased use in this species really coincides with temperate countries or European aquaculture. But you can see Vietnam within the last 2 decades has increased along with these other different species that you probably don't recognize here. So here are 3 of these species. Here we have Pangasius, what we're going to be talking about later, another eel-like fish, and a different type of strange catfish. And so these are all tropical species that occur in Vietnam. And they have one characteristic in common, is that they breathe air. And so if we look at a bunch of different aquaculture species that breathe air, that's what these are here. And this has been published in Lefebvre in 2014. And we compare all these species combined into air breathing species total. And you can see it has outpaced our conventional or temperate species, being salmonids, which are trout and salmon. And if we just look at these 2 species, so salmonids versus Pangasius, and that's that catfish, and we can look at what we know about these animals. And here we can see the number of publications that have come out for Pangasius, just been about 600, as opposed to trout and salmon, which is about 450,000. So there's a big discrepancy about what we know about these animals, and this lack of knowledge, I guess, is because of their recent emergence in terms of their economic importance. And so my thesis here is going to try to address some of these issues, or this knowledge gap for Pangasius, and what we know about it, and how some of this knowledge can be used for agriculture, or aquaculture. So here's Pangasius, and I'm just going to go over a brief overview of how I guess its road to fame. So in the 1980s, it was discovered that this fish, or not discovered, but it's documented, published that this fish can breathe air. And it's been thought to occur in hypoxia, or the evolution of the ability to breathe air to occur in hypoxia. So, and that's low oxygen. So when the environment has low oxygen, or the water has low oxygen, this fish can simply go to the surface, take a gulp of air, and consume oxygen that way. So it uses a modified gas bladder. And so typically in fish, this is used for buoyancy, so it's just a hollow balloon. But in this fish, here's a cross section of it. You can see it's very complex. It's with a lot of vascularization. So this has been modified for not only buoyancy, but it's for use for absorbing oxygen. So around that same time, in the 1980s, the Vietnamese government underwent these programs to encourage the use of Pangasius in aquaculture ponds, or not aquaculture ponds, but in just rural household ponds. So this is a poster, and what it says is 1 house, 1 fish, 1 farm. So it's pretty much encouraging farmers to grow rice like this, so they have their farm, and then throw in fish, and pretty much throw in Pangasius, because Pangasius can breathe air, so it's hypoxia tolerant. You don't have to worry about it. It's a low maintenance crop. You can pretty much throw it in your rice paddy, and at the end of the season, harvest the rice, drain the field, and you've got got fish as well. And so this is the goal of this is to provide nutritional security for these rural communities and also supplemental income in just sort of local markets. And you fast forward to today, this is a commercial pond in which you can see these guys rolling around in a boat. So these are workers, and they're feeding the fish by dumping these pretty much, like it's a 50-pound bags of food just over the side, and they'll row in a circle here. You can see this is the trail here, and behind them are just fish jumping out of the water. And these ponds are packed with such high density that as fish come to the surface to feed, more fish from below them actually push them out of the water, and so you'll see them actually bouncing along the surface as fish below them are coming to the surface to eat. And so this is just to emphasize more on the magnitude of these projects. This is a warehouse of food right here. And here's one of our colleagues, Gam, right here. So this is just enormous amount of food going into these commercial aquaculture ponds. And on the outside comes out frozen fish fillets. And so it's really this sort of vertically integrated industrial system now, and not necessarily for local consumption. If you look at the wrappers that come out, a lot of them say, are English. So if you go to Albertsons, you can buy swai, and that's what we're talking about here, this air breeding catfish. You can't call it catfish because the American Catfish Lobby has trademarked that name. So if you see swai or other types of whitefish, it most likely is pangaseous. So there's been this transition from these rural environments in which you really can't control the environmental parameters into sort of this commercial aquaculture pond where you will have not only this pond, but you have pretty much a grid of ponds in the background, and they're pretty high tech now, so they can monitor oxygen, other parameters, and measure and regulate. And so they have this ability now to standardize different environmental conditions that they didn't have earlier. What's also changed is that they're no longer for sale on local, or they are for sale, but most of the production is actually exported on these large scales. And so what you have here is an inability to really control environmental parameters, and here you do. And any small changes you make can have extreme any small changes you make in the environmental parameters in terms of increasing efficiency and how these animals behave and grow can really have huge effects on sort of the international economic scale. And so, I guess, despite that, sort of the assumption that these fish don't require oxygen and still can just live in these patties and do fine without supplemental oxygen, that notion has really continued into these commercial modern-day farms. And so this happened until 2014 when Lefebvre et al. Published this paper looking at pangaseous farms and what happens when you add additional oxygenation to the water. So here we have growth rates, and here we have 60% saturation, and here's 100% saturation. And so you can see growth rates increase with additional oxygen. And you can hear food conversion ratios decrease. So you're able to feed these fish less and still have the same amount of output. So it's showing that these fish maybe were surviving in hypoxic water, but once you remove that hypoxic stress or change in environmental conditions, maybe these fish aren't trying to wrestle to get to the surface as much, they're not spending as much energy going up and down, and really can put that energy towards growth instead. And so what this demonstrates is just by simply changing the environmental conditions that these fish inhabit, you can really have these changes in outcome that are really important to farmers in terms of, I guess, how quickly you can harvest your new stock of fishes and how much it costs to grow them to a specific size. And so this demonstrates application of basic biology, just learning how these animals interact with their environments and how this can increase efficiency of industry, economic development, food security in the region also, and also increase sustainability of these industrial practices. And so these are some of the goals that I hope to address, I guess, from the broader impacts of my dissertation research, which is not going to look at oxygen, but instead going to look at CO2 and same fish, pangaseous here, and how CO2, or how pangaseous interacts with CO2 in its environment, and whether or not decreasing the amount of CO2 in these ponds can really benefit the growth and production of this animal. And so the reason why I picked CO2 is because not much is known about CO2 and air-breathing fish. Trout have been used for probably 4, 5, 6 decades, and so we know a lot about trout and what CO2 does to these animals. It negatively impacts growth and food conversion ratio, and the guidelines of what these trout should be raisin and thresholds of survival have all been worked out. So here's healthy populations of trout, about 2 millimeters of mercury. 4 for the guidelines for survival and growth. 8 is probably what's acutely harmful to the animals. And polluted water, this is where you don't want to put your fish at all, at 19 millimeters of mercury. And this is a pengaceous pond, so 38 millimeters of mercury. And that's just standard of what these animals typically inhabit and grow and are harvested in. So right away you can see that these levels are not applicable to this animal. So this animal has shown that it can be productive in levels of CO2 that are really lethal to other animals. And so this is, I guess, fish really living in a high CO2 world. And so my thesis is going to address whether these animals are thriving in this environment or they're merely surviving. And if you decrease the CO2 in these ponds, are there implications for increased benefit and productivity in terms of aquaculture? So my thesis is divided into 3 chapters, and there are sort of 3 different angles I'm going to be approaching this question about how hypercapnia affects pangaceous. First one is going to look at respiration, so how do oxygen uptake, changes in ventilation, and what drives respiratory drive affects pangaceous. The second chapter is going to look at behavior, so is this animal going to avoid certain levels of CO2, sort of indicating whether this environment is favorable to it or not. And the last chapter, chapter 3, is going to look at stress biomarkers. So we're going to take blood samples and look at just standard indicators of stress in the blood to see if these animals are stressed by high CO2. And all of these hopefully will tell us if high CO2 is harmful to this animal, and if decreasing it has implications for or has an impact on health and production. So the first chapter is going to look at respiration. And just quickly we'll go over what respiration, or how respiration occurs in fish. So fish have gills, and on one side we've got blood, here we have the gill membrane, and the other side we have water. And oxygen diffuses from outside in the water into the blood, where it's converted by metabolism into CO2. And CO2 builds up in the blood and diffuses outwards into the water, where it has a lower concentration. And so this happens in the water. CO2 binds with oxygen and produces these other species, or these other ions here. And so what happens is CO2, every time you add CO2 into the water, it goes this way into these ions. And so it really has a high capacity for you to be able to dump CO2 into the environment without building up CO2 to harmful levels. So it's been thought of as this infinite sink in which you can just continue to drop CO2 without raising the PCO2, or the partial pressure of CO2 in the environment. And this has been thought, so oxygen has been thought to be the more limiting factor in aquatic environments, where you're able to deplete oxygen much more fast than you're able to saturate the water with CO2. And so this leads to this model here, where oxygen is extracted, or the evolution of air breathing is to hypoxia, where they could consume oxygen from the atmosphere and release CO2 into the environment, aquatic environment, as shown here. However, in hypercapnia, where we have high CO2 in the water, there's no longer this diffusion gradient outward, and so CO2 is going to build up in the animal unless you can excrete CO2 or offload CO2 by another means. And so air breathing is one method, so you can exhale CO2 into the air. Another method is to increase your internal CO2 higher than that of the water and then maintain this outward diffusion gradient into the water. So B. One problem with this is that you also have this reaction with water inside the blood, and as CO2 dissociates into hydrogen ions, you have an increase in hydrogen ions, and that creates an acidic environment, or acidic blood, also known as a respiratory acidosis. So you have a low pH. So this animal, if you want to continue to excrete or release CO2 into the water, you have to be able to tolerate a low pH. So my first chapter looked at how CO2 offloading is maintained in hypercapnia. Is it maintained by air breathing in this animal, or is it maintained by increasing blood PCO2 and then releasing that into the water? Is respiration used to cope with hypercapnia? Do we see increased air breathing with more CO2 in the environment? And is oxygen uptake changed? So the reason why we're going to look at oxygen uptake is because it is an indicator of how much energy they're expending. So if this animal is becoming agitated in a hypercapnic environment, you expect to see increases in oxygen uptake. All right, so this work took me to 2 different countries. First one's Vietnam, where I was able to work with a variety of different species and really experiment with different techniques and different animals. And then once I had that kind of nailed down, I went to Denmark to actually run the trials with 3 different species. But it was a lot of fun. It was pretty complicated. We were using bimodal respirometers, so able to measure oxygen and CO2 exchange into the air and the water. And so we made a lot of these measurements of gas exchange and respiration, ventilatory rates. And not only Pangasius, but here's like knife fish in the system here. But I was able to do it on a variety of different species. And we don't have time to talk about, I guess, the comparative study, which is what it was. It was a comparative study looking at different animals and how each animal does things differently. We're just going to look at Pangasius here because that pertains to sort of the whole of my thesis here. And so here's the data on respiratory effects on Pangasius. So first of all, we're going to look at R here. So, or I guess the open bars is normal CO2, and the red bars are going to be what happens when you put this animal in a high CO2 environment. And the first graph here, R, this is the amount of CO2 released into the air, normalized for the amount of oxygen, okay? And so we can see there's almost no CO2 released into the air during normal CO2 levels, and then once you increase CO2 levels, the amount of CO2 released into the air increases. However, the ratio we're looking for is about 0.7, so if you hit that ratio of 0.7, that means all the CO2 is being released into the atmosphere. So only about half of it is. And so what that means is if half is going to the atmosphere and the other half is going to the water, then there is this downward diffusion gradient from high PCO2 inside the body and low pH to this gradient outwards. Although there is an increase, it might just be passive gas exchange as this animal surfaces to acquire oxygen rather than to release CO2. And then this animal is mainly regulating CO2 offloading into the water using method B shown here. And just to back that up, we can look at air breathing frequency, and you can see with the introduction of high CO2, we don't see any increase in the amount of air breathing it's doing. So it's not really increasing the rate of ventilation as it encounters high CO2. And lastly, oxygen consumption. There's really no change. So this animal is not increasing its activity or metabolic rate in CO2 environments. And there's just the summary, bullet point summary. But aquaculture implications. So here is what our takeaway message is that CO2 does not affect respiration in this animal, and that CO2 also does not affect activity. So chapter 1 showed no change in terms of, from a respiratory physiology aspect, in terms of how CO2 affects this animal. If we look at behavior, so animals are known to have this avoidance behavior, or fish more specifically, to unfavorable conditions. So here we have just a theoretical tank here in which one side is low oxygen, one side is going to be high CO2, and the middle is going to be just normal water, great conditions. And what happens to these fish is that they're known to have this avoidance behavior, and so they'll leave environments they don't like, particularly low oxygen, high CO2. And if they don't, if oxygen is too low, they could die. And so this has not been well studied in air-breathing fish who are able to survive in hypoxia by air breathing. And so my question looks at, do air-breathing fish have this avoidance behavior? And is it influenced by the ability to breathe air? And so we can have a fish and look at avoidance behavior with the ability to breathe air, or we can take away the ability to breathe air. And this is a net we put